Push That Rock with Simpson Math. We defined sequences as mappings from some subset. We said it'd usually be the natural numbers and go to the real numbers. It might be some subset of the integers. So there may be some domain that's a subset of the integers. We use this symbol to represent the natural numbers 0 and all of their opposites. And we said it would go to the real numbers. In this case, we have a sequence here where the natural numbers 1, 2, 3 are being mapped to this shape, a geometric shape of some sort, a pattern of blocks. Okay, but we might ask, okay, for every input, how many blocks are there, in which case would be going to numbers in that case. So it doesn't have to be real numbers. It could be a pattern of blocks. But you can turn it into real numbers frequently, like I will here, and say, oh, okay, well, in case 1, there's 4 blocks, and case 2, there's going to be 9 blocks, and in case 3, there's going to be 16 blocks. And your question might be, how many blocks are there later? But it'd be helpful to make that count, to look at what's happening. What happens from case 1 to case 2 and from case 2 to case 3? And you might notice that case 1 is kind of hiding in here. Here, I'll shade it. There's case 1. So what happened? Well, 2 blocks fell on the end, and then a block fell on top of each pile. Did that happen again? Well, sure it did. Here's the 2 blocks that came down on the end. And then we had 1, 2, 3, 4, 5 piles here. 1, 2, 3, 4, 5 piles here. And each one got 1 stack taller. So here was case 2 hiding under here. And what happened to it was a block fell on top of each one. And then we had the 2 on the side. So you could imagine what's going to happen next. And you could even start to count what's going to happen next. So in the 4th case, we should get 2 blocks on the end. So we're going to add those 2 in. But we're also going to add 1 for every pile that's already here. So there's already 1, 2, 3, 4, 5, 6, 7 piles. We're going to add 1, so that's 7 plus 2 more. We're going to add 9 to however many are here already. 16 are here, so we're going to add 25. And that's what we should see in case 4. So what this gives us is a situation where we know it's quadratic. Well, how do we know that? Well, we get these common differences. If this was always the same number, if I said 9 minus 4 and got 5, and then 16 minus 9 and got 5 again, and that kept going, we would say, oh, it's linear. You know, remember we said it was arithmetic if you could add the same number each time, but we're not adding the same number each time. Let's see, 25 minus 16, that's 9. But notice what does happen. If we get what's called the second difference, we are always adding 2 more than we did before. That's right, we add 1 for each stack, but then we always add the 2 on the end. So we're always adding 2 more than we did before. Well, since this, not the first difference, but the second difference, instead of a first degree polynomial, i.e. linear, i.e. arithmetic, we have a second degree polynomial that would describe this pattern. Well, we know what second degree polynomials look like. They look like this. They're quadratic equations. We know that when we put in 1, when we put in the output, maybe I should have used n's instead of x's, but when we put in 1 for the input, the output should be 4. And when I put in 2 for the input, it should be 9, and 3 for the input, it should be 16. So I put in 1 for the input, I get out 4, put in 2 for the input, get out 9, put in 3 for the input, and get out 16. And then I simplify this. Well, you know, these 1's go away. I just had 1a plus b plus c equals 4. 2 squared is 4, so I have 4a, and then 2b, and then c equals 9. And then this 3 squared is going to be 9, so I have 9a here, 3b, so 9a, 3b plus c equals 16. So here is a system of equations. And we could solve this system of equations. In fact, we learned how to solve system of equations. We know how to do Cramer's rule. We could set this up as 1, 1, 1, 4, 2, 1, and 9, 3, C, and this would be our D. and we'd get the determinant, and then we'd plug in 4, 9, and 16 for the coefficients here, get d sub x and so forth. So, but I don't want to do all that. Okay, but I'm just pointing out you could solve a system of equations and figure out what the coefficients a, b, and c are, plug in the a, b, and c into the quadratic equation, and you'd have the quadratic formula that predicts the number of blocks that are in the nth case. So what is the nth output? Well, you'd have a formula for however many blocks are in that case. But I don't think we need that high-powered deal there. I think we can just figure it out. So let's think about it. So the way I'm going to think about it is I'm going to think about what would be case 0. What would case 0 be? Well, remember you're supposed to add 2 blocks to the end. So case 0 would just be 1 block. So from here, you would have the 1 block, you'd put 1 on top and put 1 on either side. So how does that help us? Well, it extends our table. Remember our table was 1, 4, 2, 9, 3, 16, 4, 25, and now we have 0, 1. Okay, so that helps a little bit. So here's our n and here's our a sub n. And we have those outputs. But let's think about it a little bit more. Since we know it's quadratic, we'll think about the case. Now, here's our case 1 right here, and case 0 is this guy, and we figured out this would be case 0 because you'd add 1 to each end. And then, so what is case negative 1? What would case negative 1 be? And for that matter, what would case negative 2 be? So now we're saying instead of going from the natural numbers, we're including the whole numbers, and now I'm even going into negative land. So I'm saying, well, maybe I'm going to start from some point in negative land, so I'm going to start for a subset of the integers. Well, I see here the basic quadratic. It goes through 0, 0, where our 0 is going through 1. So when we're at 0, we're going through 1. And when we're at 1, we're going through 4. So we're all the way up here at 4. What do we think maybe the next point is? Would it make sense that the next point is nothing? Maybe there's no block here. I wonder what case negative 2 would be. Can we think about case negative 2? Well, maybe case negative 2 is start the pattern over again, maybe going down. Maybe instead of having the blocks, maybe put a block lower down. Maybe case negative 2 is a block down, and then the next case after that, negative 3 would be 2, 2 drop. So it's dropping down. If we think about it maybe that way, then maybe we already know the equation. Oops, missed it. Maybe we already know the equation of this parabola that looks like this. Maybe you can tell me that that's a parabola shifted to the left 1, so it would look like this. So when I put in 0, for x right here, I get 1 block. And when I put in 1 for x, I get 1 plus 1 is 2, 2 squared is 4. Oh, what happens if I put in 2? Well, I get 3 squared, which is 9. 2 goes to 9. What happens if I put in 3? Well, 3 plus 1 is 4. 4 squared is 16. Oh, it goes to 16. What happens if I put in 4? 4 plus 1 is 5. 5 squared is 25. So see, we didn't have to resort to some advanced algebra here. We could have done it, but we didn't have to resort to that advanced algebra. We can think this out, and we can realize, oh, a sub n is simply n plus 1 being squared. Math made simple. It's Simpson Math.